You know, for over 2,000 years, one single book has been the bedrock of logical thought. And it wasn't a religious text, it wasn't a collection of laws, it was this quiet, methodical book all about lines, circles, and shapes. And yet, its impact on science, on philosophy, on how we even think and argue today is, well, it's almost impossible to overstate. Today, we're going to unlock its secrets. So, what is the most influential textbook ever written? I mean, you could make a case for a few, right? But a really, really strong case can be made for Euclid's Elements, written way back around 300 BC. Now, our guide for this little journey isn't some ancient scroll, but a specific hard-working edition from 1885. And this quote is from its preface by a guy named John Casey, an Irish mathematician. You see, his goal in 1885 wasn't to replace Euclid. Not at all. It was to present the unrivaled original in all its integrity. He got that the real power of this book wasn't just in the answers, but in the process. And that really gets to the heart of it. Euclid's Elements was never a list of facts to memorize. It was a system, a blueprint for how to build undeniable, rock-solid truth from the simplest possible starting points you can imagine. All right, let's dive in. Section 1, a blueprint for thought. We're going to see how the system literally built the modern mind. So, how do you do it? Well, that's our next section, the building blocks. The whole thing rests on what's called the axiomatic method. It's kind of like starting with the most basic Lego bricks to build an entire universe of logic. Let's look at the very first piece. And I mean, it does not get more basic than this. This is from Book 1, Definition 1, a point. It has a location, a position, but no size, no length, no width, no depth. It's a pure idea. It's the first tiny, indivisible atom of this logical world we're building. Okay, so from a point, we build the next piece, a line. A line is what you get when a point moves. It has one dimension, length, but still no thickness. We're still in this world of pure concepts, just carefully stacking one idea on top of the last one. So this is it. This is the whole machine, the Euclidean method, in 4 steps. First, you define your parts, things like points and lines. Then, you state your postulates. These are the basic moves you're allowed to make, like drawing a line between 2 points. Next up, the axioms. These are universal, self-evident truths, like the whole is greater than its part. And only then, only when you're standing on that solid foundation, do you start trying to prove things, the propositions. Okay, theory is one thing, but now let's see this beautiful system in action. This is the art of the proof. The challenge sounds simple. Create a triangle where all 3 sides are perfectly equal. But here's the catch. We're not allowed to measure anything. We can only use our established rules. So we start with postulate 1, which lets us draw a straight line from any point to any other point. Boom! We have our line, AB. Next, we use postulate 3. That one says we can draw a circle from any center with any radius. So we stick our compass point on A and we draw a circle with the radius AB. Now here's what's cool. Every single point on this circle is now a proven distance of AB away from point A. No guesswork needed. And now for the magic. We do the exact same thing from point B, and that new point C, right where the 2 circles cross, that's the key. Think about it. By definition, point C is a distance of AB away from A. And it's also a distance of AB away from B. So all 3 sides, AB, AC, and BC, they have to be equal. And just like that, a perfect, provable truth is built from nothing but a few simple rules. Just brilliant. Now, that thing we just did, that proposition, that was what Euclid called a problem. It's about doing something, constructing something. But he also had theorems. And those are propositions where a property is demonstrated or proven. This difference is so important. Euclid's system isn't just a toolkit for building stuff. It's a framework for proving timeless truths. So let's jump forward in time again, back to our 1885 edition. We're going to talk about its upgrade and how this ancient text became a living document. So Casey wrote in his preface that he wanted to connect Euclid's unrivaled original with the, quote, modern conceptions and developments of geometry. He basically saw that the method was absolutely timeless, but the applications could evolve. He wanted to make this 2,000-year-old book a totally vital, relevant tool for the students of his time. To do this, he didn't just reprint the original. He added something. In fact, he added more than 800 of them. So what were they? He added over 800 new exercises. And these weren't just random busy work. They were carefully chosen problems designed to challenge students and show them how to apply that classic Euclidean method to the geometry problems they were facing in the late 1800s. This totally transformed the book from a historical artifact into a living, breathing workout for the logical mind.
Okay, let's bring it all home. What is Euclid's enduring legacy? Why does a 2,300-year-old book still shape our world?
Just think about it. The scientific method? That's pure Euclid. Start with a hypothesis, gather evidence, build to a logical conclusion. What about legal arguments? Start with established laws and precedents. Apply them logically to the facts of a case. Computer programming? It's literally building complex systems from fundamental commands and logical operators. Even philosophical reasoning. All of these, they're all echoes of the axiomatic method. They are all blueprints for thought. And that leaves us with one last, kind of big question. Euclid built his world on axioms about points and lines, things he took to be self-evidently true. So what are the unquestioned axioms we are building our world on today? What are those fundamental assumptions that are holding up our science, our societies, our own beliefs? And maybe more importantly, what happens if one of them isn't quite as solid as we think?